right, so we can now begin. Last week we have seen an intercolor with some fine examples, and I have also indicated a candidate way of asking a question. In fact, the concept was to model the color receptors of a human eye with some shapes. So those shapes could be arbitrary in a question, and they could be way easier than the actual human perception, which is just maybe a more complicated way of drawing some receptor functions in terms of wavelength. So we have our receptors and we have our light sources, and those light sources may also contain some sort of bandpass shape in the wavelength domain. So matching a color that would look exactly the same to the human eye as another color, a natural color, is the key idea for color signal processing or color image processing in the form of color reproduction. Now today we will continue with the whole image processing in an hour or something. I'm saying image processing because in many of the books that are called digital image processing and things like that, people just focus into these and they explain it, elaborate it, and make examples of those. But this is a graduate level course, and those things are mostly undergraduate level. So we will see some undergraduate level image processing, but we will be quick about that. And the fundamental concept that we will start with will be called image enhancement. And I'm warning you that this is image enhancement for the human eye. So it looks good, it looks better for our eyes. But image enhancement is not for computers. So if you are doing an automated image processing, like pattern recognition or image recognition, object classification, and things like that, those are things that computers do. And for those things, in a majority of the cases, the enhancement things that we will be talking about do not really enhance the image, but they actually deteriorate the image. But it looks better to our eyes. So we do it that way. And we will be learning how to do it that way, according to the human eye. But still, in a lot of papers that are submitted to journals or conferences, whenever people are doing some automated computer application of image processing, like image classification, they start with an image pre-processing, and that pre-processing they claim to enhance the image. And in a majority of those cases, they are wrong, actually. They are not enhancing the image. Whatever you do to an acquired image, it is most probably disturbing or spoiling the image even more. For instance, it may have some noise, and you are eliminating the noise. While eliminating the noise, you are most probably eliminating the features that you're also looking for. So pre-processing is, in many cases, there are some exceptions, of course. If the noise level is too high, then the simple image processing techniques like edge detection and things like that may fail. So in order for them not to fail, you have to, of course, reduce the amount of noise. But other than that, if you are smart enough in doing your image processing, the pre-processing stage is doing nothing good for the rest of the process for computers. So be careful about that. Don't jump into the concept of, let us do pre-processing of the image. Why are you doing that pre-processing? Because it looks better. But, yeah, okay, it may look better, but for classification, the computer does not care. For instance, we will see the contrast stretching. We will start with that one, actually. Let's give an example to that. Contrast stretching. Stretching. So the image contrast is low. It's mostly grayish image, so it doesn't look good. And we cannot notice the details of an object, for example. If it is higher contrast, we will see it better. But the computer does not need that. The contrast, as long as the contrast is there for the rest of the process, for image classification, segmentation, for instance, the computer will see it, put a threshold in an appropriate place, and make the process. So this is an unnecessary process, for example, for image enhancement. For whom are you enhancing? If you're enhancing for the humans, this is good. So it's more artistic, let's say. The contrast stretching usually looks good if the histogram of an image is condensed in a narrow range as opposed to the full dynamic range. So we have some intensity levels. We're talking about an intensity image here. If you are applying it to color images, you must look at the luminance channel, the intensity channel for the contrast. You shouldn't do these operations on individual red, green, and blue channels, because if you alter the RGB channels in a different way according to their dynamic range, then the eventual output color will be different. A bluish thing will look like a yellowish or a greenish, maybe reddish kind of thing. So do not make the processes, do not make the transforms, do not do anything on individual RGB channels. You have to first transfer everything into YUV kind of thing, where there's an intensity and two color difference spaces, and you do your process on the luminance and on the intensity. So this is the intensity channel. Even the sampling is done like that, by the way. We have seen JPEG, for instance, which where in actual implementation of JPEG, there is a subsampling, downsampling going on, and that downsampling is applied differently on the luminance and the color channels. The color is downsampled by 2 times 2 or 4 times 4, reduced a lot, but the luminance is not downsampled that much. It's not downsampled a lot because the details are there, but the color details are not significant to the human visual system. So you can downsample them a lot and then upsample them and then merge them to reconstruct the RGB values. It will still look sharp enough. So we are working on the luminance channel. And the luminance channel is, let's say, 8 bits. So the minimum value is 0 and the maximum value is 255. What is the thing that I'm drawing here? This is like the value of the pixel, and this is the count of that pixel, which we call as histogram. So we have to know what an histogram is. First things first. A histogram is you look at the count of how many pixels are there inside your image with a value of 0. That count is plotted as the magnitude of this function at the value of 0. Histogram at 1 is the number of pixels inside the image with a value of 1. So it's a counting phenomenon. And it is also, it also corresponds to, after the normalization, the proper normalization, it corresponds to the probability density function, actually, of your two-dimensional function, your image. It's the probability density. All right, so this is your histogram. If it looks like this, then you see that this point of A and B are the darkest and the lightest points of your image. So what you can do is you may want to improve the visualization of this one, visualization only, because you cannot really alter anything for the recognition processes, as I have indicated before. What you can do is you may want to stretch this dynamic range of not so dark, darkest place and not so bright, brightest point with a so-called curve. You can apply an input output operation which maps your pixel values to different pixel values, but every time you have one value, it is of course mapped to another value, so the amount of values do not change. How many values do you have, for example, for this image? You have b minus a many different pixels, obviously, from this image. From this histogram, I can see that in the image, there are b minus a many different types of pixel intensities. The output variation will be the same. There will be b minus a many pixel values always. You cannot change the amount of variation of intensities, but you want to spread them for A being the minimum and B being the maximum available. What is the minimum and maximum? They are 255 and 0. So the input is ranging from 0 to 255, and the output is also ranging from 0 to, let's say, 255. Let's assume that they are the same points. If you do an input-output curve in this format, up to A, you map every pixel value to 0, including A. And then from A to B, you map every value according to this line function, and you map everything beyond value B up to 255 to a value of 255. So this is a curve, okay, that we can apply. So if your pixel value is, for example, this one, x, and x is mapped into a new value called x prime. You can write some analytical expressions of that x prime if you wish. X prime is equal to I don't have the the formula right now, but it's like x minus a first, and it is scaled by this curve. So let me get rid of this because I didn't think of that formula for the time being, but it's a simple formula. It's just mapping everything between A and B to 0 and 255. A is mapping to 0, B is mapping to 255, that kind of a mapping. It can, I think, be analytically expressed in one line as a mathematical expression, but I cannot think of it right now in the morning. Maybe I need to have a breakfast first after that. I mean, start writing the formula, but as of now, I am unable to. So this curve is essentially increasing the contrast because the lightest, the brightest point will be observed to become white, and the darkest point will be observed to become black. And it looks better when you do this kind of a thing. In general, if you want to increase the contrast, what you do is you do a kind of a curve from 0 point to 255 by 255 point. If your curve is, and this is the linear curve, by the way, okay, that line corresponds to doing nothing. The input is the same as the output, 45 degrees mapping for input to output. If to the center of it, if it stays below like this, it makes dark portions, the lower gray values, to become even lower, okay? So in a sense, it's increasing the contrast in the dark sides. And if you do this kind of a curve on the bright sides, it makes the bright gray values to become closer to white values, larger than their original values. So the brights will be brighter and the darks will be darker if you apply this red curve. If you apply a curve like this curve will make the whole image look darker. If you apply this curve, it will make the whole image to look brighter. Okay, and this the last one, which is sort of green, is also, it has been used in many of the screen shapes in the old days, where the tube screens, the tube TVs, CRT, cathode ray tube screens were used for computers because of the nonlinearity of the intensity mapping applied by the screen itself. It is already doing it in the blue way. So in order to make it normal looking, we further apply a green profile of a curve while seeing it or observing it on the screen to make it a little bit brighter actually, and then it looks correct. But nowadays the screens that we have, the flat LCDs and other flat technologies, they are very good and they don't need these kinds of things. So we usually apply it at the input stage to look at it better. In biomedical images, for example, this is a good thing because many of the doctors may want to focus to some point, some region of a radiological image where they want to depict some details, and in that contrast range, they may not see those details. So they want to increase the contrast to see it better. Sometimes they use it like that. So this is called contrast stretching, and in Photoshop-like things, like applications, these are easily applied using a tool called curves, which is these. These are curves. So on the menu, if you select find curves, this is what it really does. And you can even apply these straight curves as I did at the left-hand side of this graph. Now, if the contrast stretching is doing automatically, it is called histogram equalization. Histogram equalization is an automatic way of expanding the dynamic range into the full range, okay? And it's even better than that. For instance, I was doing this linear mapping between A and B, but even those things could be fine-tuned and adjusted in such a way that everything between A and B is mapped not only to 0 and 255, in between 0 and 255, but becomes as uniformly distributed as possible. Clearly, for a discrete counting process like a histogram, it's not possible because, for instance, the number of this pixel, let's call that pixel C, okay, the pixel value C, the number of pixels inside an image with value C is that much with the red bar, okay? And if you map it to another value, this count will not change. So that bar will certainly be as tall as that red bar, but it will move to the right or to the left. And another pixel value, let's call it D, will have that many pixels inside the image with that value. And that height will not change, but it will move to the right and to the left. So how can we make a uniform distribution, uniform PDF, like a uniform histogram? And you will immediately realize that for a discrete and finite image, it's impossible, technically speaking. We cannot do that. But what we can do is to consider, we can consider the histogram or the density function to be within a window. For instance, I will draw this in red. There is this C, which is mapped to somewhere else, and the D is here, and E is here. They are moved like this, so they are separated a little bit. And then we can observe that within a region of delta, if you can count how many pixels are there within this delta range, you will see, well, the height is that much, whatever that value is. And if you move that delta to around the previous pixels and take a look at how many pixels are there with these values, then it would be the combination of the summation of the two shorter red counts. Okay, they will be combined all together or added in the same delta range. So as you see, although technically the peaks are different, the density of the lower pixel counts will be more. They will be densely packed together to count as something larger, whereas the longer values will be isolated, will be left away from these bars. You see, these bars are discrete, actually. We don't have a continuous curve here. These bars are discrete bars, and when you separate two bars, there becomes an emptiness, a gap between two bars. So we stack the shorter bars together so that when you look at them within a region, their combination will give you a high value, and the taller bars will be isolated a little bit. So their total count are still a lot inside the delta range. I hope I'm making myself clear. This is how we are going to convert the histogram to a uniform histogram, so-called uniform. If you look at them point by point, they are, of course, not uniform. They are not the same. They are different lengths. And there are even zeros between. Everything that I did not draw corresponds to zeros. So a large one, then 0, 0, 0, 0. If it's, of course, not uniform. But on the average, you are making a moving average sliding window. And that sliding window gives you something more or less constant throughout the range from 0 to 255, let's say. So this is what in discrete time the histogram equalization will give you. And in your final examination take home, by the way, I will be asking you to write a histogram equalization software in MATLAB. You can find them, but most of the histogram equalization routines that you will find will be too much professional. I don't want you to just copy those things and submit them as exam questions. I want you to write your own program in a lousy and sloppy manner, like we always do in writing MATLAB codes, because we are not professionals, we are not software developers. We're just trying to observe some phenomena. So our MATLAB programs are usually quite simple and trivial with some loops and things like that. In professional MATLAB programs, you can never find loops because loops are very slow in MATLAB. They do it in a vector notation, but that is something quite alien for us. So I will ask you to do it, to make an implementation, but what is it? Let me explain. And I want you to make the implementation of that explanation. Well, that explanation comes from, fortunately, from something in continuous mathematics. And it comes from a PDF. Well, it's not a portable document format. It's probability density function, okay, from probability. The PDF is the distribution that we have, like the histogram, as I say, but it has some nice properties. Suppose that you have this kind of a PDF from a minimum to a maximum, and those minimum and maximum are considered to be between 0 and 1. So that is the normalization, and it's a continuous variation. Let's call this PDF to be equal to the density function to be equal to R. And PDF has one nice property, an obvious property. Since it's a density function, when you integrate or find the area under the density from -infinity to infinity normally, you will get 1. So the area under the PDF curve is equal to 1. Okay, that is the PDF. And but it's not R really, it's the PDF of R. So let me write it like F R of R or something like that, okay? And this is R essentially. Now we will make a mapping from R to S. So R is our random variable and S is our new mapped random variable. We are applying a function to R. You can write it like S is equal to a function of R. Okay? And or R is the inverse function of S, where S has the PDF to be constant. So this is the Fs of S. Okay. So the PDF of S is uniform. There exists a mapping which makes it a uniform uniformly distributed random variable. So what is that mapping? Is the thing that we are looking for, and that mapping is something algorithmic. It will become to be algorithmic, and that algorithm is called, when you discretize that a little bit, it will be reflected to become the histogram equalization. Now, since S is equal to a mapping of R, the PDF of S will be equal to the PDF of R times dr by ds evaluated at R is equal to inverse mapping of S. This is a mathematical expression of what happens to the probability density function when you apply a mapping. Okay, you can check this formula or something similar, analogous to this formula from the book by Proakis, for example, the famous probability book. And the nice thing is that we want to make this thing to be equal to 1, which is uniform. Okay? So this value is, of course, 1, because the range is between 0 and 1, and the area underneath is 1, therefore the value is also equal to 1. We want this thing, this formula to happen, but the thing is, how does it happen? Let's write it again. Fr of R, times dr by ds is equal to 1, which tells me Fr dr is equal to ds. Okay, I'm cheating a lot here. I mean, of course, you cannot write these things like this, but I'm bypassing a lot of in-between stages, and I'm just trying to motivate you about the eventual formula that I will have, because the eventual formula is correct, by the way. So you have this kind of an expression, and you just integrate the right-hand side and the left-hand side of this equation. And the right-hand side of the equation becomes S. But it is an S of R, of course, like T of R, okay? It's the function that is applying to R. And the left-hand side of the equation, I'm integrating like this. It is the integral from essentially minus infinity, but everything starts at 0. So it's from 0 to R. I'm integrating fr of an auxiliary variable I have to use. Let me use gamma, but it was a bad one. So let me draw it again, a gamma, d gamma. Okay, this is the way that we integrate. And this, therefore, left-hand side is the process, the histogram equalization process that we have to apply to map every R into S of R. And that mapping, as you see, is quite interesting because it is using the probability density function, or like it's using like the histogram. So this is the PDF, which is equivalent to the histogram. Here, this is the value of the pixel, and we are accumulating, or we are integrating from 0 to the value of the pixel, all the PDF or all the histogram. So how does it work? Let us make an illustration on this PDF. Suppose that the value of R is here. So what will be S? This R will be mapped to an S value. What is that S value that this R value is mapped? And then what will you do, by the way, after doing this mapping? You will search for all the pixels inside the image which has the value of R, and you will one by one replace all those values by S inside the image. They don't have to be localized, they can be sparse. So the histogram does not give you any information regarding where these values are or what the image is. It is just the density function, okay? So this point is R, and we want to find S. What is S? S is this area. So the area is equal to S. The mapping. R is mapped to S. R is between 0 and 1, as you see. It is given to be between 0 and 1. And that area that I have shaded in red is also between 0 and 1, because if I shade everything, it will be 1. The total area will be shaded to 1. So this much is clearly less than 1, and it is positive. So it's something between 0 and 1. Anything between 0 and 1 is mapped to something between 0 and 1. If R is less, from here, as you see, if R is a smaller number, then the corresponding area will also be smaller. If R is equal to 0, there will be no area and it will be mapped to 0. So 0 is mapped to 0. If you increase R all the way up to 1, that 1 value will be mapped to the area underneath, which is, again, 1. So 1 is mapped to 1, 0 is mapped to 0, and everything in between is mapped to a value between 0 and 1. And as R increases, the accumulated area is also increasing. That's how the idea of the histogram equalization works. Suppose that your probability density function is a different one, and it is like this. Something like this. So this is 0, this is 1, and the distribution is like this, and the area under this triangular shape is 1, because it's a PDF. Fr of R. When you choose your R value here, let's call this R1. What's the area under that? From 0 up to R1, the area under this curve is 0. So R1 is mapped to 0. This, if you choose this, it is also mapped to 0. So anything less than this value, which is the beginning of the triangle, is mapped to 0, which is good because we want to really map this point, which is A, by the way, this A point to 0. And after that, after A, we want to map it to some certain things. For example, this point of R2 is mapped to this value of the area, whatever that area is. But when we come all the way up to B, what is B mapped into? Can you tell me? You can write B, the value of R is equal to B is mapped to what? I'm asking you now. You may write, you may open your microphone and tell me if you're listening to the course. Are you with me? One. Okay, thanks, Ozan. Yes, B is mapped to 1, which is the highest value. And after B, anything here, let's call this R3, is also mapped to 1 because from 0 to that point, the area under this triangle is still 1. So A is mapped to 0, B is mapped to the maximum, which is 1. That will make a perfect mapping from R to S, where the probability density function of S with this kind of mapping for this random variable will become uniformly distributed between 0 and 1. Okay, that is how we do the equalization of the PDF. Now we have equalized PDF. We haven't equalized histogram yet. But histogram equalization from here, or the discrete histogram case, is simple. What you do is you just normalize the histogram to count up to 1. Normally, let's say the total number of pixels, total pixel count, let's say, is equal to n. So there are n pixels. It may be, for instance, 1000 by 1000, then n is equal to 1 million, which means that if you sum up the histogram curve, you will find 1 million. 10 of those 1 million will have this value, 15 of them will have that value, etc. And so you just divide every count to approximate R of Rk, let's say, to be equal to the count of k divided by n. So it will be between 0 and 1, and the total count will become 1 using rational numbers or real numbers, of course. Now, this time I'm not working with integers, but you can also make an implementation which actually corresponds to the integer numbers as well. Then Sk, which is the mapped version of Rk, is essentially all the pixels counts from 0 up to k of those nj's, the counts of those pixels, divided by n. So this count will give you from starting from the first count up to the kth count that you have, it will give you the mapping. So you're not integrating, but you're summing all the histogram bars up until some point, and you divide all of them by n. This will be the value of sk, between 0 and 1, and you may want to scale everything by, let's say, 255, again, to make it between 0 and 255 instead of 0 and 1. Because it may be an 8-bit intensity, so the values are essentially not between 0 and 1, but you must amplify them between 0 and 255, and that sk is then that value. You have to convert them back to integers, of course. So this is how you do it. Okay. The histogram equalization. This is, I gave it as an example, but actually this formula is the histogram equalization formula that we have, and it's what you're supposed to do. It's interesting. So look at that. The value of sk is not related to the value of rk. Look at the right-hand side of the equation. Do you see the value of rk at the right-hand side of the equation? No, sk is not determined by its previous value. It's not a mapping that is related to the previous value, but it's a mapping related to the histogram, to the distribution, where that previous value is putting a boundary, and I'm finding the area under the histogram, which is some summation, and that summation is the value of sk, the mapping. I find it interesting. That's interesting. It's not really a function of rk, actually. It's a function of the histogram. sk is a function of histogram, because we are trying to have sk to have, we want to make sk to have a uniform histogram, as uniform as possible. Please remember the things that I have indicated. It's never uniform. It can't be in discrete time, but it is as good as it gets, let me say. Sorry. So this is the histogram equalization. And if I were you, I would really work on this a little bit. In X-ray images, for example, the contrast is very low, and sometimes you really need to do histogram equalization. Okay, now, do you have any questions regarding this histogram equalization? When I ask you to write a small program to take a test image, a grayscale test image in MATLAB, for example, and apply histogram equalization and print the histogram equalized image on the screen, will you be able to write that kind of a program? Because only if you understand how it works, you will be able to do that. If you don't understand how this works, then you will have to copy from internet without knowing what it really does. And trust me, I understand that one. I can guarantee or assure you that I will understand a MATLAB code which was written by you or your friend or someone in a similar level of MATLAB knowledge, or something that you find from internet. It will look awkwardly different. So I will know it. Don't do it that way, please. Write the MATLAB code by yourselves. Okay, now I'm opening a new page, and I will quickly continue with sharpening concept, and after that we will give about half an hour of break. Or we can start by smoothing. And it's an insult to explain smoothing to an electrical engineer with such simple and stupid ways, because we know Fourier transforms, we know digital signal processing, we can design filters in an extensive way of varieties, but smoothing is therefore some term that is used for the noobs, let's say, for people who are not familiar with mathematics of this signal processing, but they want to do image processing because images are popular or they need to do it. So people mostly use some smoothing kernels like this. There are 5 pixels here, 5 neighboring pixels, 1 in the center and 4 at the immediate neighbors, top, bottom, and left, right neighbors. 4 neighbors, in other words. And we give a value of 1/5 to each of these, and we convolve with this thing, with this template. It is certainly a smoothing filter. It's a low-pass filter, but it's not a very good low-pass filter. If you take a look at the Fourier transform of this 5-pixel shape, you will see that it's far from being ideal, but it's depicting more of the lower frequencies, and high frequencies are less in magnitude. So it is really a low-pass filter. So you can use it for smoothing, but it's more like blurring. Or a 3x3, 9 pixels, which is the center plus the 8 neighbors this time. The diagonal neighbors are also contained, and you give a value of 1/9 to these, and you will have a blurring operation. These are very typical, but of course, to make them better or sharper low-pass behavior, you actually need some wider smoothing filters, not as narrow as these ones, and you have to adjust their values. For example, it's always a good idea to give some higher emphasis on the intensity of this convolutional template at the center pixel. For instance, in the left-hand side, those 5-pixel case, the center pixel may be 1/5, sorry, 1/2, not 1/5, but 1/2, a larger value, and the rest are just 1/8. So when you add them up, they will give you 1/2. The summation of the pixel values in a filtering template must be equal to 1 if you don't want to change the intensity, the overall intensity. It must be normalized to 1. So the sum of these values must be equal to 1, but the center value may be larger. And there are better, of course, blurring or smoothing filters as opposed to this one. Sharpening. It comes from a gradient operator, a difference or a derivative operator of a 2-dimensional surface. Normally, we know that if you have a continuous surface function of f of xy, so at the coordinates of x and y, it attains the value of f of xy. So it's a surface function. The gradient of this, I'm putting a bar underneath because the result is a vector. Because we know that in 2-dimensional shapes, surfaces, the gradients are essentially vectors. But we will be trying to, let me put these curly parentheses here to indicate the operator. We can assign a gradient operator without a bar, indicating that we are looking at the magnitude of this gradient vector. Like this, the magnitude of the vector, which is actually the partial gradient or partial derivative of f with respect to x plus partial derivative with respect to y, all squared, and then added, and you take the square root of it. This is the natural way of finding the magnitude of the gradient, but it's too difficult to take magnitudes and things like squares and then square roots, etc. They are computationally difficult. So let's try to estimate them even further. By the way, this is this thing is delta fx, and this is delta fy. Let's give those names for further processes. Instead of delta fx square plus delta fy square and taking the square root, I may just add the absolute values of these. Of course, this is incorrect, but it's approximately the case. That is estimating the sharpening operator. By the way, this delta f by del x can also be further approximated. So delta fx is an approximation by itself as in discrete time fxy minus fx minus 1 y. So it's the first difference that I'm taking to call it delta fx. And similarly, delta f by del y is approximately equal to fxy minus fxy minus 1. It's again a first difference. And I'm putting these into these equations. So it's an approximation within another approximation within another approximation, etc. These first differences can be backward differences, like x comma y is here and x minus 1 y and x comma y minus 1. This is a backwards first difference, but forward first differences could also be used clearly, like x and y are here, and this is x plus 1 y, and this is x comma y plus 1. This is a forward first difference, and you can also use the differences between the forward pixels. Or some better gradient operators could even be proposed. A nice gradient operator which does not use 0 degrees and 90 degrees differences, but instead of them 45 degrees rotated versions like this. And this is quite brilliant, by the way. This is xy. This could also be applied to forward or backward 45 degrees, but I'm just using the forward case here. It's easier. X plus 1 comma y plus 1. This is x plus 1 comma y. This is x comma y plus 1. So the gradient will take the differences between these two and these two, like this. So gradient magnitude square, I will need to take the square root of this, or I may use individual terms, absolute values for further simplifications if you wish, like this, fxy minus fx plus 1 y plus 1. So this is the 45 degrees difference, or minus 45 degrees actually difference. And the other 45 degrees difference is the difference between fx plus 1 y minus fx y plus 1. The difference between these. This is also a gradient of some sort. You can use it in this format. It's known as the Rubert's gradient. Okay. Now these gradients are not doing the sharpening. Now we have only seen some gradient operators up until now. So how can we use them for sharpening purposes? We can use them in various ways. For instance, we can say that fxy prime, the sharpened version, is equal to fxy plus a fraction, let's say a times gradient at fxy. And there are alternatives of gradients, as we have seen. So we may add some part of this gradient into our image. That may enhance the sharpness. In terms of our visual system, of course, it's not really making a sharper image. It's impossible to do it with these methods. This sharpening is not really sharp. It only looks sharp, okay? Be careful about that. Another operation that can be used, it all depends on how it looks and what's your application, what's your purpose. It's like gradient of f of xy can be directly used as the intensity if the gradient is greater than a threshold and you use the image itself else. So if the gradient is too much, you use that too much value as the pixel. Another one, these are alternatives, of course. You can use a constant level of gradient if the gradient is greater than a threshold and the pixel itself else. You can use the gradient of let me just say the gradient because we know what it means as of now. The gradient itself is if the gradient is greater than a threshold. These thresholds are not the same, of course. They all depend on your applications. And a background constant value else. The last one is mostly used for operations like edge detection and things like that, because it gives you constant values throughout the image, and it gives you some emphasized intensities only along the gradient points. So these are the operations that you may do, but as people who know signal processing, for us, for our purposes, these are what you can do is you can design a two-dimensional filter along the frequency axis and say that I want to emphasize, so I want to have lower magnitudes, but I will increase the magnitude to larger values like this. Excuse me for the poor graphical illustration. So it's like a plate shape Fourier transform magnitude I'm talking about. So it's the magnitude is h of omega 1 and omega 2. So you may design your own filter which emphasizes higher frequencies a little bit more and suppresses the lower frequencies. That would give you a sharpening filter probably better than all these things, but it will be mathematically speaking or computationally more expensive because the convolution will be difficult. These gradient operator convolution operators are, as you see, all 2 by 2, very short operators. It performs very fast on the images. But if you want to do accurate sharpening with some formal filter design techniques using signal processing, those filters will be larger filters and their operation upon the image will take longer time. But the result may look better, of course. We will talk about other intensity transforms, stack order filters like median filtering and things like that, which are nonlinear mostly, and some other further techniques. They will all continue. It's now 10:36. Let's give a break of about half an hour. So at 6 past 11, 11:06, let us meet. Okay, and until then we can give a break now. So I will stop the recording. I will close the meeting and we will meet again at this hour at the same place. Okay. If you have any questions, you may collect those questions and ask them in the beginning of the next hour. So until then, take care. I'm closing now.